Okay, so now for the next several lectures, I think up to lecture number 10 or something. So after having learned all the basis of deep learning, what we're going to do is that we're going to use it for solving PDEs. So this is sort of the main content of the course because it's after all, course on deep learning for scientific computing. And PDEs are a very important part of scientific computing. Okay, so let us start now. So what are PDEs? So I assume that many, if not most, if not all, most know what PDEs are. But before that, why are they important? And in that context, let me share a quote from Herbert Simon. So Herbert Simon won the Nobel Prize in Economics in 1978. And this is his quote, okay? So it's a long quote. You don't have to follow each of it. But the most important thing is the following. Much of the activity of science is an application of the following paradigm. So given the description of some natural phenomena, it could be anything, it could be sound propagating in this very room. It could be how we are heated up in this room from the heating somewhere. It could be anything that you can think of, why lightning forms, why clouds form, and so on. So any scientific phenomena, the key is that you find a differential equation for the processes that will produce the phenomena. Okay, so essentially what he's saying, and this is not me, this is a Nobel laureate from 1978, what he's saying is that all of science follows the following paradigm. Given a phenomena, you model it with a differential equation. And I just paraphrase it because instead of using generically differential equations, I say use a partial differential equation. And these are PDEs, right? So that's why they are very, very important. There's a large amount of phenomena in sciences are modeled by them. So what's a PDE? So just for simplicity, let me give you a simple example. So now you have some domain here, D, which is contained inside Rn. And it could also include time, okay? So this could also be a function of time. And U, the solution of this PDE is going to be some function, okay, perhaps better to take it as domain. So it's a mapping from D to R, just scalar valued functions. So in other words, this is a function of, let's say U is the function of T and X. X stands for space and T stands for time. And then you have the normal notation for derivatives. So you can take UT, UTT. So these are partial derivatives, right? And so on. Similarly, you take the gradient of U. So the gradient of U is all the, so UX1, UX2, up to UX, maybe n minus 1 in this particular case. So you have a vector, the gradient, you take the second derivative, and so on and so forth. So these are the derivatives. So you have a function here. You have all its derivatives in both space and time and space. And then what a PDE does is the following. So you take some relationship between capital F, which depends on X, it depends on T, depends on U itself, on the gradient, on the time derivative, on the second derivative, on the second time derivative, and so on and so forth. This is equal to 0. So this is the generic form of a PDE. So in other words, what a PDE does is that given information about a function or relationship between a function, its gradients, its second derivatives, and potentially higher order derivatives. So this is an implicit relationship. What we have to get is find a function U. Okay. So this is what a PDE is, or solving a PDE is essentially inverting this implied or implicit relationship and then finding the solution. And we will see several examples today, in the next lecture, in the lecture after, in the lecture after, and so on. We have lots and lots of these examples. But now you see, so this is the sort of notation. This is where we stand. And most importantly, the reason why we study PDEs is because from everything that you have, all the way from the subatomic scales to the universal scales, to everything in between, are described by PDEs. Okay, so now who can tell me what kind of PDEs describe things at an atomic or subatomic scales? So what's the most famous PDE that can describe things like, this is some nanomaterial, right? So it's some organic material. What kind of PDEs can describe structures at this scale? Does anyone know? No, Boltzmann. Now you're looking at subatomic. Boltzmann is also important, but not, you'll see that later. But subatomic, what's the equation? Yes? Schrodinger equation. Very good. So this is the Schrodinger equation. Schrodinger. I almost always get the umlaut in the wrong place, but I think I'm correct here. So what is the Schrodinger's equation? Schrodinger's equation, so for instance, for electrons, so this is electrons, electronic structure. I'm not going to write equations for everything, but let's take one of them, right? So what does it say? It says that the wave function psi, so this is psi is what is called the wave function. It describes in some sense the probability of finding the electron at certain locations and at certain momenta and so on. All of you should know this from chemistry or physics. This is equal to h of psi. So I is the unit imaginary quantity, psi of t. So this is the time evolution, and h is the so-called Hamiltonian, which is, let's say it's given by minus Laplacian of psi plus some potential, which depends on x and t. Okay, so this tells you the forces that are acting on this. This could be electric forces, this could be magnetic forces, depending on the context. And this is sort of, it tells you the diffusion of this wave function. So this is a very important example, and it is widely solved. So in the subatomic or electronic and protonic scales, we have the Schrodinger's equation. So this is the first example. The second example, so this is at the tiniest scales, and the largest scales that we can consider are at universal or galactic scales, right? And here is, of course, a typical example of this. So this is a thing that all of you might have seen in the last couple of years, 3 years ago. So we have two binary black holes, or two black holes rather, which are sort of merging into each other. And because they're merging into each other, they're essentially ripping apart the fabric of space-time. When they're doing so, they generate gravitational waves. These waves are coming out, and these waves are detected, for instance, at the LIGO detector. So what describes this entire process of the merger of black holes and then sort of the ripping apart of space-time and generation of waves? There's a very famous PDE that describes this. So who can tell me that? Come on, all of you must have read the news, right? So what happened? Yes, Einstein's equations. So here you have Einstein's equations. And as all of you know, although he did not write these equations in this building, Einstein certainly studied here. And this I'm not going to write down because that will take me several slides to write down, right? So this is another example of a PDE at the other extreme. And as you can see, simulating that is very important if you want to do astronomy and astrophysics. And so these are the two extreme scales that you have, but there are also things that are happening in between. For instance, the thing that affects us a lot is our own climate. So here is a simulation of the climate. There are many things that govern the climate, but the most important bunch of equations that you can get are some version of what are called Euler or Navier-Stokes equations. We will see these equations time and time again. So these are also examples of PDEs. So these are at the scales. These are still at large scales, but not as large as the universe. But nevertheless, they're all described by PDEs of various complications of various hues. But the same kind of PDEs will come in again and again. And one of these PDEs that will come in repeatedly are the Navier-Stokes equations of fluid dynamics. Or in these particular cases, another version of it, which are the Euler equations. Euler equations also have a very strong Swiss connection because Euler himself was Swiss. And then in between, so remember that from the small scale, so the smallest scales, which are below the scale of atoms to the scale of our cells, for instance. So here is an equation which describes, or here's a physical problem or a biological problem, which describes how the wing of a fly, so you have it's the same process that takes when we are ourselves forming as infants, not as infants, but as embryos. How the wings of a fly is formed, and this is governed by something called the reaction diffusion equations. Reaction diffusion equations, or some version of reaction diffusion equations. And this particular equation I'm very proud of because I wrote it down myself, so I modeled it. So but the point that I'm trying to illustrate is that you have different kinds of equations which occur in at different scales, spatial scales, time scales. But the important thing is that look at the various gamut of phenomena that you have looked at. So subatomic scales, so let's say material science, chemistry, then you have astrophysics here, climate science, and this is biology. And then, of course, all of engineering is somewhere in between. So all these things are modeled by PDEs. So their study is of great importance to us. And the thing about PDEs, which makes them so interesting, is that none of these PDEs, not even except in the very, very simple cases, you cannot find exact solutions. So given a PDE, you can't just write down a formula. If you could do that, that would be miraculous. But for instance, Einstein did that with his equations in a very, very simple case, barely, even that barely. So you can only do it in very, very special cases. So in general, you cannot find solutions to PDEs as formulas explicitly. So what do we do in that case? So what we do in that case is we use what are called numerical methods. So here I call traditional, but there's nothing traditional about them. So numerical methods, historically, they came up in, let's say, there were some early versions of them in the 1870s, but I would say that they came up around 1920s. So they've been around with us for 100 years, and that's why the name traditional in this context. And numerical methods are what you solve these PDEs, for instance, the Schrodinger equation or the Einstein equation with. You cannot solve the Einstein equation by hand. You have to use numerical methods, and they come in different guises. So you have finite difference methods, finite element methods, finite volume, collocation methods. And since we also have time, there could be different kinds of Runge-Kutta methods for time integration. So these are, it's not even enough to learn this in one course. You need several courses to learn all traditional numerical methods, right? So in that sense, it's quite a large topic. You don't have to know traditional numerical methods for this particular course. If you have any questions, you can always ask me. Hello, yes, you have a question? Okay, yes, go ahead. Everyone ask. No. I know what finite elements are and what they are not. Don't worry. This is but it could be finite element. It could be finite element. This is finite element because the elements are clearly marked out, but this could be finite element, but it isn't. Okay. Okay. So now what's the point about? You don't have to learn these methods in this particular course. In fact, the course is somehow the complement to traditional numerical methods. However, almost all the data that you'll be given for your projects and your exercises, this will be generated by traditional numerical methods. So if you have some insight into traditional numerical methods, it is helpful, but it's not essential. Now, as I said, this is 1920s and we are in 2023. So in 100 years, these methods have, of course, matured. They have, people have used them in all kinds of contexts. So as I said, we don't have to learn all about them, but I'll still give you one simple example. For those who don't know this, maybe many of you know this, I'll just do a very simple PDE, which we are going to use extensively, and I will write down the method associated with it. So the PDE is going to be the heat equation, or some people also call it as the diffusion equation. So we are in 1D. So the domain is D is 0, 1 cross 0T. So now you see, so this is your domain in space, this is your domain in time. And the PDE itself, this goes all the way back to Fourier, if not before, and this is approximately 1800. So this is the following. So UT, so now U, the solution of this could be, for instance, the temperature. And this is a function of space and time, right? So UT, the time derivative, is equal to the space double derivative. Okay, this is the heat equation. I'm not going to derive it or anything, just take it from me. And then, of course, something has to happen at the boundaries, otherwise it's not well posed. So now I have 0T is equal to U of 1T is equal to, let's say, 0. So in other words, I put some ice on both corners. Okay. So I put some ice on both corners, and then there's some heating source, or I start with some initial temperature and see what happens. And then, of course, we also need some initial conditions. So let me call this a U bar of X. So this is a heat equation. It's a very simple PDE. We are going to see it several times today. So now what we did in the PDE is that the time derivative equals the space double derivative. These are what are called boundary conditions. And these are what are called initial conditions. Okay. So now given some initial conditions, something here, you have to find the solution for the rest of the domain. So this is, in this particular case, I can write down a solution, which by hand, and this was already done by Fourier. But I can easily make it change the problem slightly so that you can no longer do it. Now, what does a finite difference method do? Just to give you some idea of what goes on. So what a finite difference method does is that it has to discretize, right? So as you can see, and this becomes very relevant in a few weeks. So the inputs here are functions, right? So what are the inputs? Okay, this is for instance, the initial condition, u naught or u bar. This is a function. So it is some function that is given to us. And outputs are also functions. So input, for instance, is u bar of x. And output is also a function. I should just use the same color. And this is the solution, u at different times, right? So remember, so for a PDE in general, the input is going to be a function and the output is going to be a function. And this is what we are going to process. However, means our computers are digital, so it's not possible for us to give continuous inputs and continuous outputs, and they will remain so till we have quantum computers, for instance, where we can give we have to give discrete inputs and discrete outputs, except if you have quantum computers where we'll have continuous inputs and outputs, but that's a different story. At the moment, we are condemned or restricted, whatever you call it, or even blessed to be in a digital world. So things have to be discretized, which means that nothing can be continuous. So the domain has to be discretized, the inputs and outputs both have to be discretized. So if you do that, so what do you do? So instead of having a domain, which is a continuous object, so this entire, let's say, space, this entire plane here, what you do is that you break it into tiny points. So D cross D is discretized or is approximated by a bunch of points in space and a bunch of points in time. Okay, so this is what you can see here. So I have divided this interval, the unit interval, into small pieces, and I take some points, and these points are defined in the following manner. So I pick a delta x. This is called the mesh size. And this object here is what determines how many points are there and what is the distance between them. Similarly, I do the same in time. Okay, so I have delta t, which is called the time step. And so instead of having now continuous quantities for the domain, what I have done is that I have discretized them into these discrete pieces. So that's the first thing that we do. So we also have to discretize our inputs and outputs. And for that, we do the following. I call it as V. So V of xj. Okay, let me write it as the following. So yeah, so let's say that u at xjtn, this is approximated by a quantity that I'm going to denote as Vnj. So now instead of having continuous objects as my input and output, I always have them discretely. So I have vectors if you want, or an array if you want, and so on. So what is my input now? Input is this vector V0j. J is the dimension, the number of mesh points that you have. And my output is going to be Vnj for all n, for 1 less than n less than some capital M here. And how are they related to each other? So the inputs and outputs are both discrete quantities. One is a vector, the other also can be reshaped into a vector. I have to relate them from the equation here. So this guy here has to tell me what it's going to be. So I have to approximate ut, and this I do effectively just by taking a difference, a finite difference. So I can call it like this. And similarly, this quantity here, uxx, I'm going to approximate it with a spatial second difference, right? So you can do Taylor series, j plus 1 minus 2 vnj plus vnj minus 1 delta x squared. Okay, so these are both smart choices, as you will see, or reasonable choices. So what I have done is, if I'm sitting at this point, instead of computing a time derivative, which I could have if I had access to continuous objects, what I do is that I compute it by just taking the difference between these 2 points and dividing it by delta t. Similarly, instead of computing a spatial second derivative, which I don't have access to, what I do is I go one step to the left, one step to the right, add them, take the difference twice this value, and then take delta x squared. So now, as you can see, when I equate them together, then I'm in a good shape because I can write the following scheme. So this implies the following: Vn plus 1j. Now, believe me, it's very simple calculation, is 1 plus 1 minus 2 delta t by delta x squared, Vnj plus delta t by delta x squared, Vnj minus 1 plus Vnj plus 1. So this is a numerical method, a very simple numerical method that you can teach in 5 minutes. But let's look at its processing. What does it process? So if you give me V0j, like some values here, this values here, this values here, I can just use this formula to get this value. And similarly, I can fill up like this. And once I have the values at the first time step, I can go to the second time step, third time step, and so on, till I reach all the time steps. So this is, it's very simple to write it down. It's coding it up takes less than a minute if one is proficient in Python, for instance. Okay, so that's a good thing about it. And this was already known for a long time, since the 1920s, that instead of looking at a PDE in a continuous manner, you can have this kind of a discretization. So that is good about it. And it is precisely these kind of ideas that in some form or the other are also underlying more complicated methods like finite volume and finite element. But this is a different story. I don't do it here. Now, what is the caveat here? So what one can learn, well, let me just add a page here. Yeah. So again, you have to more or less believe me. So remember that I had this equation, ut equal to uxx, and my solution is u of xt. My numerical method, on the other hand, was this object here, which is 1 minus 2 delta t by delta x squared of Vnj plus delta t by delta x squared of Vnj plus 1 and Vnj minus 1. So this is my numerical method. And then one can look at the error. Yeah, and what is the error? The error, for instance, can simply be, okay, maybe I shouldn't put a norm here, but something like this. The error, for instance, can be something like this: summation over j delta x of u at xjtn. Not that we know the exact solution, of course, minus v and j. So this I will call it as ej, sorry, en rather, not ej, because it depends on time. And then I can say E is equal to maximum over n. E delta x is maximum over n, E n. And then one can show that E delta x, it behaves like order of delta t plus delta x squared. One can show this. This also won't have taken me much time. It would have taken me 5 minutes to show this, but I don't have those 5 minutes. Okay, so what does it tell me? It tells me that if I take more and more points in both space and time, then clearly I have more and more better representation of my continuous objects. And because I have better representation of my continuous objects, the error that I'm making by going between the continuous and the discrete, this error is going to get smaller and smaller. So in particular, as delta t and delta x square go to 0, my error is going to be 0, right? So in other words, I'm able to approximate my solution of the PDE by this finite difference scheme. Now, why did I say all this? By the way, due to some other considerations, stability. So delta t has to be like delta x squared, roughly speaking. Therefore, the error will actually behave like order of delta x squared. Okay, so this is let's remember this for a second. Now, the issue here is that this was just in one space dimensions. Suppose instead of having one space dimensions, I have two space dimensions or three space dimensions. What do? You can repeat the same process. For instance, if you have ut is equal to uxx plus uyy, you can repeat a finite difference. You can easily write down a finite difference scheme. But now you can imagine that instead of having a unit interval, I have a unit square. and I'm dividing it like this. And the number of points now, it scales like order of delta x. Okay, the other way around. So let's say that the mesh spacing is the same in both directions, delta x, then this will scale like 1 over delta x squared, right? So the number of points changes in one space dimension, it scales linearly with respect to step length. In two space dimensions, it scales quadratically with respect to step length and so on. So if you have d dimensions, and this is going to be important in a second. So ut is equal to Laplacian of u. And what is the Laplacian? So Laplacian of u is nothing but summation j from 1 to d of u xj xj. So you take the gradient, the second derivative, the Hessian, and you take its trace, or you add all the components in each normal direction. So if you do that, so then remember that the number of points scales like 1 over delta x, or delta for that matter, d plus 1. And why is it d plus 1? Because you have d dimensions, but there is also time, right? So time, okay, actually I should be careful here. It's not true. So the number of points scales like 1 over delta x to the t, 1 over delta t, right? Because in time also we have delta t time steps. So as you can imagine, the number of steps that are needed to reach up to some final time is given by 1 over delta t. But now delta t itself scales like delta x squared. So the whole thing is like 1 over delta x to the d, 1 over delta x squared, which means that the number of points finally scales like 1 over delta x to the d over 2. But remember that the error does not depend on the dimension. The error is constant. It's not like in 2 dimensions or 3 dimensions, I have better error. The error is always going to be constant, and the error is going to scale quadratically with the mesh size. On the other hand, the number of points, and this tells you computational work, right? Because remember, when I do this, I have to do several iterations, and for each set of points, I have to do these iterations. The number of the computational work is at least proportional. It is more, but at least it's proportional to the number of points. So for the same amount of error, roughly speaking, you can see that the computational work keeps on increasing as dimension goes, right? And in particular, it goes exponentially. Or in other words, bottom line is work scales, or the other way around. We can say work scales error. Maybe, let me write it down. Work grows exponentially with dimension. And the reason why I introduced it is because this produces, or this sort of creates, one of the big problems with traditional numerical methods. It's well and good when you're in 1 space dimensions, 2 space dimensions, but already see in 3 space dimensions, you will start seeing that it becomes very expensive. And in 4, 5, 6, 7, 8, 9, 10 dimensions, this becomes prohibitively expensive. So the amount of work, so instead of having 100, you go to 10,000, then you go to 1 million, then you go to 1 billion, and so on. So this exponential growth with respect to dimension, and this is going to be a big issue as we proceed. Okay, so this is not the only issue. So this tells us that high dimensional problems are going to be particularly problematic because the error is going to grow exponentially in dimensions. But this is not the only issue. There are other issues. For instance, if you are very complicated, so now remember, if I just had a square, it's sort of trivial to divide it into a mesh, right? But now just imagine, so this is from my own lab, so I know how difficult this is. So this is just the sort of nose end of an aircraft, okay? And you're going to make of the fuselage, and you're going to make a mesh around it. And to generate this mesh, I did it myself. It took me approximately, it's a very high quality mesh. It took me approximately 4 or 5 days. I'm not kidding. It really took me 4 or 5 days, many years ago, but 4 or 5 days to get a sufficiently nice mesh, because there are different, as you can see, there are many, many points here, there are less points here, and so on. So it takes some time. But in a commercial context, like if you go to any company, engineering company in the Zurich area, it takes anything between a month and 6 months to generate a proper 3D mesh to get good results. So this is also prohibitively expensive. There are many other issues. There are multi-scale problems, multi-physics problems, and so on and so forth. And of course, as I said, dimension is critical. And someone said Boltzmann equation. So Boltzmann equation, this is already, you're already out because it is 7-dimensional. Remember that the error scales exponentially. So 7 is a very big number. And then there are some, Schrodinger in particular can be hundreds or thousands or tens of thousands of dimensions, because it does not depend on the physical dimension. It depends on the number of electrons that are there in the system. So this is, if you have a complicated molecule, you're already out. And there are many other problems where the dimension is large. So it is not like these traditional numerical methods. They are very successful, but they come with their own caveats. And let me just illustrate a little bit more about what sort of problems they really fail in. So another set of problems where it's problematic in some sense are what are called as many query problems. This is precisely the set of problems for which machine learning is supposed to help us. So what does many query problems mean? Let me give you an example. So again, it comes from engineering, in this case, design. And you want to design, in this simple case, just an airfoil, not a full aircraft, but just an airfoil. So an airfoil is just a cross section of a wing. So this is the airfoil here. And what you want to do is to change the shape such that some aerodynamic properties, lift, drag, and so on, these aerodynamic properties are optimized, right? So how is it done? So what is done is that, first of all, the shapes themselves have to be parameterized. Sometimes they're not even parameterized, but people have worked for 50 years to produce good parameterizations of these shapes. So the design parameters are roughly 50 parameters. 50 parameters. We just tell you how the shape can be varied. So there's a design space, and this is how the shapes are going to be varied. Now you have to optimize, right? And this can't be done by hand. You can't just guess which shape is going to be aerodynamically correct, right? This is not possible. So what people do is the following. So you take a let's say starting shape, and then for each shape, you have to solve the underlying equations. In this case, these are what are called compressible Euler equations. And this simulation for this simple example takes approximately 20 to 30 minutes. Okay, maybe it can be done if you are willing to sacrifice resolution 5 to 10 minutes. But then the point is that it goes through an optimization loop. So for each step, you have to make slight small changes in the shape space so that you get better aerodynamic response, right? And you might have to do it anywhere between 1,000 to 5,000 times. And this has to be done sequentially, because the previous shape is the next shape is an improvement of the previous shape, and so on and so on and so on, right? So each time you make these changes, so what you do is this small incremental changes, just like you did with gradient descent learning. But now, each time you call the shape, you also have to call the solver for computing the lift and the drag. And this takes approximately, let's say 15 minutes, just to give you a number. But now if I do it 5,000 times, 5,000 times 15 is still a very large number. Now this is in 2D. Imagine if you do this in 3D, right? Remember that it grows exponentially. So pretty soon, you see that this becomes prohibitively expensive. So much so that a commercial aircraft manufacturer like Boeing, it spends approximately $3 billion each year on its simulations alone. So this is where this is the cost, 3 billion, Boeing alone for simulations, which is to do these kind of calculations many, many times. So many query. So many times the PDE solver is called. So multiple calls to a PDE solver. The PDE solver is the numerical method that is approximating a PDE. So just imagine that instead of having 15 minutes, if you can do it in 1 second, how quick the design process is going to be, provided that this is going to be accurate enough. Okay, here is another example. This is something which is also quite interesting, which is an inverse problem. So these are the sort of problems that we will try to solve in the course. So this is what actually happens. So you're interested in measuring or calculating the properties of the rock. down. For instance, if you want to do hydrocarbon exploration or mining exploration and things like that. So how is it done? So what you do is you have a truck which has some vibrator that is going to throw in waves into the subsurface, and you put a bunch of receivers. So during a campaign, it will start here, it will put in the waves. Now the waves get reflected, right? And transmitted depending on the subs, and they get recorded like this. And you keep on doing this at different locations. You send in waves. These are waves which follow the wave equation. So this is the PDE that you have. And this is how it is done. This is not a cartoon. This is reality. So you have UTT minus 1 over some c squared of x, Laplacian of u equal to 0 plus initial and boundary conditions, essentially boundary conditions. So this is more or less a boundary condition. And then you take these measurements, record them at the different measuring stations, and from this you get some sort of a data file which looks like this. So essentially here is time, and these are the different locations, and this is how this is. And from this you have to invert and get the rock formation, which looks something like this. Now this process is also based on optimization, just like design. And each time you do this optimization step, you have to call a solver for the wave equation. And in 3D, this takes a long time. In fact, in 2D, even in 2D on a problem like this, to get anything close to 10% accuracy can take you easily several hours. Okay, and you can imagine how the cost scales in 3D. But again, what is the issue here? The issue is that you have to solve the wave equation multiple times, and you have to do it sequentially. Because if you could do it parallelly, you could do it on different computers and probably get some speed up. But in this case, you have to solve it sequentially because design is an iterative process. Similarly, but this is at least you can parallelize. So this is uncertainty quantification, another very important engineering problem. And what is uncertainty quantification? So here is a sequence of simulations. These are all done in my lab here. And this is, let's say, the most, this is the 1024 cubed simulation. So 1024 cubed means that you have, so approximately the number of degrees of freedom for this is 10 billion per time step. And you also have thousands of time steps. So this is a computationally very heavy problem. So you can see this is a very, very complicated flow, right? It has all kinds of eddies and whirls and so on and so forth. But a single flow is useless because what happens if you make the tiniest perturbation, because it's sort of a chaotic system, you'll get a completely different response, right? So it's not enough in any engineering context, design context to solve it once. People want statistics. They want to compute like mean, variance, maybe some higher order statistics. And these are the objects here. But this requires something like thousands of these simulations. Okay, thousands of these simulations. And there comes the little secret here, right? So now you can parallelize because these simulations are not dependent on each other. They're no longer sequential. And for many years, 10 years, we have designed a code which is sort of really optimal on GPUs and so on. We take this code, we put it on Daint. This is the biggest machine that we can have access to. And still, we have to do this. You can't do better than this to the best of our knowledge. But still, we have to do this simulation 1,000 times roughly. And if you start costing it, you know, what is the cost of a single simulation just to produce these answers? It was $1 million for a single simulation from an academic group. So these are the costs that we are dealing with, right? Because these problems, they are effective to some extent. Some cases, they are not even feasible, but they're effective, but they're extremely expensive. And this expense really prevents us from doing good design, good science, and so on. So essentially summarizing, and then we can take a break. So traditional PDE solvers, again, I'm using traditional as if these are outdated. By no means that is the case. They are state of the art, and people do research on them actively. So what is the issue with traditional PDE solvers? So this is right here. So for many query problems, it's computational cost. And it's not just computational cost, it's very high computational cost. So reducing this is going to be very effective. Sometimes it's impossible. Like, as I said, for a high dimensional problem, Schrodinger's equation in 100 dimensions, you can't do it. You have to do approximations. People do approximations. But so there is no feasibility for certain problems. They are unfeasible or infeasible. Okay, so in particular, high dimensional problems. And I told you why, because of this exponential growth in cost. And finally, which is sometimes never said, is that many systems, we don't know the physics that well. We have some idea of the physics, but we don't know all of it, right? So for instance, typically human body is a good example. Okay, I'm working on a project where, for instance, let's say the heart is pumping out blood, right? It's pumping out blood. The blood goes all over our entire body. And the basic sort of fluid mechanics of this is relatively well known. For instance, you know that it will follow the Navier-Stokes equations. There is some fluid structure interaction because our arteries and veins are not rigid bodies. They have some structure in them. You can write down the equations, but there are still several physical effects that you don't know. So physics will be necessarily incomplete. However, we might have lots of data, for instance, patients' data from the hospital. So these are the sort of situations. So if you don't have complete physics, a physics-based solver like solving the Navier-Stokes equations is useless if the Navier-Stokes equations themselves don't describe the system in its entirety, right? So these are the cases where existing current sort of state of the art breaks down. And this is precisely the space at which the course is going to operate. Because what we are going to do is actually not all, but most of the rest of the course, what it's going to do is that we are going to find alternatives to these traditional PDE-based solvers. This is also true for ordinary differential equations, which are a particular case of partial differential equations, but let's say physics-based solvers, and this will be based on deep learning. Okay, and this is so today, tomorrow, next lecture, the lecture after, and we go on for the next 7-8 lectures. This will be the space that we are going to operate in. And what I have tried to do over the last 45 minutes or so is to give you the rationale of why this is important. And I hope that I have convinced you in doing that. Okay, so let's take a break now. We gather at 1:15, so 10-minute break. But remember that even though you don't need to know about PDEs, but all the data that will be generated in the course will be from traditional PDE solvers. Okay, and this will be an important point. Okay, so we take a short break now, and I can pause the recording. Okay, so the point about traditional numerical methods is that you have this grid and you do all these manipulations of the grid. And we have also seen that it's not so easy to sometimes generate grids, right? So for very complicated problems. Now, what we do with physics-informed neural networks is sort of a radical departure, okay? So the idea here is, or the question that one asks is the following. Can one get essentially traditional numerical methods? You'll see that this is just part of the story, but let's say that we didn't know anything about traditional numerical methods. They were never invented, but we know everything what Ben taught you in the last 3 lectures, deep learning and so on. The question is, can we forget traditional numerical methods and solve PDEs numerically, of course, only with neural networks? So this is a question that I'm asking. We don't know anything about traditional numerical methods, yet we want to solve PDEs, like the heat equation that we could solve very easily with a traditional numerical method. But of course, the cost was high and so on. The question is, can we do this purely with neural networks, end to end, right? This is the question that we're asking ourselves. And to some extent, the partial answer is provided by physics-informed neural networks. Okay, so this is an attempt, at least, to solve PDEs numerically by just using neural networks. So how is this done? Okay, so here is, I'll take my time to go through this slide because it has a lot of content, but I'll try to do it slowly. So remember the heat equation, right? This is the PDE that we have already seen. So UT is in one space dimensions, so one space and one time, so 1 + 1 dimension. So the equation is UT equal to UXX. I have 0 boundary conditions and some initial conditions, U bar, just like before, exactly the same setting that I had shown you the finite difference scheme. Now, for some reason, I have inverted the space and time here. So here is space X. So as you can see, it goes, okay, in this case, it goes from -1 to 1. There's no difference. And here is time, which goes from 0 to 1. Okay, so now the question is that we are going to solve this end-to-end using neural networks. We're not going to use a grid. We are not going to use finite differences. We are not going to use finite elements, finite volumes, whatever. We're going to do it end-to-end with neural networks. So how can we do that? So the idea is the following. It's a simple idea. So we know that the exact solution, again, I'm sort of getting my colors wrong. So the exact solution here, u, which is a function of space and time, at the very least, it's a much more regular function, but at the very least, it's what is a continuous function on your domain across 0 t. So it's at least a continuous function. We know that as a function of space and time, it's a continuous function. I don't know if Ben mentioned this or not, but neural networks are what are called universal approximators. Did he mention this or? Yes. So what does it mean to be a universal approximator? Who is going to tell me that? Yeah, since he said it, so some of you should know what. Yes, go ahead.
We should be able to approximate and compose to any function that we.
That's roughly the idea. So what a universal approximator means is that suppose I have a continuous function, for instance, u, the solution of this PDE, then, and I fix the error epsilon, then there exists a neural network. In fact, we can be very, very specific. We know how big the neural network is going to be, what sort of architecture we have. Let's say we just take multiplayer perceptrons, how many neurons we need, what's the width, what's the depth. We know concretely what this is, so what numbers this is going to be, such that u minus this u of theta is going to be small. There in some norm is going to be small. Okay, so this is what is universal approximation, right? So this means that in principle, there exists a neural network somewhere of a certain architecture, which is going to approximate the solution of my PDE. Let me call this as u theta, because it is what I don't know here is theta, right? So theta are the parameters, the weights and biases, and my neural network takes as its input x, t, and churns out a number, which is u theta of xt for different values of x and t. And somehow I'm going to say that this is going to be the solution of my PDE. Now for random values of theta or some arbitrary value of theta, sure as hell, this guy is not going to satisfy my initial conditions, right? Because you take some random values of theta, of course, for instance, in particular, so that this is going to be 0, all the weights and biases are 0. So for sure, you can't satisfy your initial conditions. So we need to find values of theta such that the difference between the initial condition, exact initial condition, and the initial condition as represented by the neural network. So along this line here, this is going to be small. Okay, is this clear? So we know that it doesn't fit the initial condition, but we try to find a theta such that the initial condition is matched. So this is what I call as, there's some terms here, but let me call it as initial residual or temporal boundary, because the initial condition is what is given at the temporal boundary. So this object here is what is the temporal boundary residual, and I'm going to minimize this mismatch by an optimization process. Similarly, for a random value of theta, I'm not going to get that the boundary conditions are satisfied, right? Because again, just imagine if you take some random values of theta, you will get very strange values on the boundary. Whereas I know from my problem that the values on the boundary should be 0. So what do? I say that I take this difference with the boundary values. So u theta minus 0, which is u theta restricted to the boundary. So this is a mismatch, and this is just a term for it. We call it as a spatial boundary residual. Residual, as the name suggests, is something that is a difference, a mismatch, right? So that's the residual. So well and good. So now I could just take these two terms, the temporal boundary residual and the spatial boundary residual, and then try to find a theta that is going to sort of optimize or reduce or minimize these losses. And then I'll have a neural network that is going to satisfy my initial conditions right here, and it's also going to satisfy my boundary conditions. But that is not going to be the solution of the heat equation, right? Because the solution of the heat equation also has to behave in some certain manner in the interior of the domain. And this is what we don't know. So now the question is, how do we find this out? How do we, of course, if we are given values of the solution in the interior, some specific points, let me use a different color. Let's say some specific points here, I could try to minimize my mismatch, right? But but this is precisely the problem. I don't know the values of the solution. Now, this is my objective. My objective is to find the values. I don't have access to these values. So I cannot use supervised learning in the sense that I cannot supervise the values in the interior, right? I have to do something else. So if you just use plain naively neural networks, this is a problem that you are stuck with. How do I find the values in the interior? And this is precisely where the PDE comes to our rescue. So remember that in addition to satisfying the initial conditions and the boundary conditions, the neural network should also be a solution of the PDE, or should be as close as possible to a solution of a PDE, right? So in particular, it has to satisfy the PDE. So what is the PDE? The PDE is, let me remind you, it's simply UT equal to UXX, or UT minus UXX equals 0. So this is my PDE, right? Now remember, my U theta is the function of x and t. So these are its inputs. And so in particular, so since I know that xt maps to u theta of xt also maps to the time derivative. And this is something that can be calculated, because what we have learned from Ben's lectures so far is that whenever you have neural networks, you can very easily differentiate through the neural network in order to calculate derivatives with respect to the hidden parameters, weights and biases, but also with respect to inputs. The same algorithm, automatic differentiation, backpropagation, whatever you call it, backprop, the same algorithm efficiently, very efficiently, almost optimally efficiently, finds the time derivative, for instance, because time is one of the inputs. So you get it. At any point here, in principle, if I have a neural network, I can use my backpropagation automatic differentiation algorithm in order to compute the time derivative. I can also do that to compute the spatial derivative. So next week, Ben is going to do this. He's going to show this code, and also in the exercises, this will be shown to you. But we can compute the spatial derivative. The spatial derivative of a neural network is also readily computable through backpropagation. If you can compute one derivative, you can compute two derivatives, three derivatives, and so on, right? You can keep on repeating backpropagation. And so in particular, you can also compute the second derivative space, because that's what you need in this context. So now I can compute this PDE residual at every point in principle. For each point, I call the routine, and I can compute this PDE residual, which will be this object here. So I just call it as a PDE residual. And remember that in general, this if I choose a random neural network, sure, it is not going to satisfy the PDE. But now, since I know how the PDE losses can be evaluated, what I'm going to do is that I'm going to optimize. I'm going to minimize these losses. So let me repeat what I'm going to do. I have a neural network, which means that at any point in space and time, I can evaluate the value of the function. I can evaluate the spatial derivatives, the temporal derivatives, if necessary, to any orders. I'll, of course, make errors in these things, but let's forget them for the time being. Let's say that I can almost do this exactly. Now, so what I'll do is that I will define my mismatch at the initial conditions, this term here. I will define my mismatch at the boundary, this term here. And I'll also define my mismatch, not with respect to any function, but with respect to the PDE, by using this automatic differentiation to compute this quantity. And these quantities can be defined by any point at any points that I want, right? So in particular, instead of having a grid, I can just take of course, I have to take finitely many points, because at the end of the day, nothing can be done continuously. Everything has to be discretized. So in this particular case, the discretization is in terms of a point cloud. So the algorithm is as follows. We are going to do it several times, but very heuristically, this is what happens. So you start by taking a cloud of points to cover the whole domain. So you just spray a cloud of points. This can be done, for instance, randomly. That's the whole point here. Do it randomly. So these are points that are in the interior. You can also randomly and independently choose points at the spatial boundaries as well as the initial or the temporal boundary, right? So you have a point cloud that is well defined. You have a neural network, which is well defined based on whatever architecture that you're choosing. And then you can define these residuals at these points. So for instance, this is the initial residual, which is given at these points here. So you have this. This is sort of the boundary residual, which is given at these points here. And the PDE residual is given at this point cloud in the interior. Okay. So is that clear? So these are the three constituent terms: mismatch, penalize mismatches at the boundaries, penalize mismatch initially, and penalize any deviation from the fact that it's a PDE. And what do we utilize to do this? We know what the PDE is, so we can always automatically differentiate through backpropagate, and we define this objective here. And now, so this is J of theta. This is some sort of a loss function that we use whatever SGD, Adam, stochastically, LPFGS, and so on. Whatever optimization algorithm that we have, and we'll at least end up with something that heuristically seems like the correct answer. Because remember that it's supposed to be only an approximation for the PDE, because the PDE solutions are unique. So if the PDE is going to be, the PDE residual is going to be 0, you'll recover a unique solution. Okay, so is this point clear? So I will repeat the algorithm in a bit, but the idea is it's in some sense different from what you do in supervised learning. Because in supervised learning, let's say you have dogs and cats, you show a picture of dog, and in training, you're always saying, okay, this is a dog. Another picture of dog, this is a dog. A picture of a cat, this is a cat. Here, you're not doing that. So what you're doing is that, of course, you have some supervision at the boundaries because the initial and boundary data are given to you. But in the interior of the domain, there is strictly no supervision. The only supervision is through the PDE itself. We are simply saying that UT minus UXX is as small as we can. So in that sense, it is a radical departure from dogs and cats type machine learning, supervised learning. Okay, is this clear? So now let us see if, so this is what is the genesis of physics-informed neural networks. Now you will see that the first thing that we have done is we have not used a mesh anymore. We have just used a point cloud, right? It's not like we can randomly, you also have to have some fidelity with the domain. It means you can't just put points on one side of the domain, right? It's all over the domain, but I could, for instance, sample them randomly. This is already good enough. So the second thing, so that's so let's write down some things, then I'll tell you the history. So this is a physics-informed neural network. It's still a neural network. All that changes now is the loss function. Okay, so it's the architecture is the same. It's no radical departure. You can use multi-layer perceptrons. You can use convolutional neural networks, recurrent neural networks, transformers, whatever you want here. So there is no change in that. What changes is simply in the loss function. So remember that it's essentially a different loss function, essentially PDE or physics informed loss function. So it's actually, it should be physics informed loss functions, but we are stuck with notations, right? So this is the main point. And actually the ideas have been around for a long time. Means if you look into, probably there have been something in the 80s. But these ideas have already been known since 1994, and certainly from 1996, 97, there were many, many different papers which explored this idea. Remember, this was the time when there was the algorithms to implement neural networks didn't even exist. People are working with shallow neural networks, not with deep neural networks, and so on. So now, then there was a hiatus, just like in all of machine learning. And after almost 20 years, it was picked up by George Kaniadakis, essentially. The idea comes from way earlier, but the engineering behind it and the realization that this can be done with modern software, automatic differentiation through PyTorch and TensorFlow and so on, was done. And today it is sort of extensively sort of used. There are thousands of papers already, I mean, more than thousands of papers. But the reason why it is so popular is, and I will give you a generic thing in a bit, is first of all, it's in principle meshless. And remember, I told you something about generating meshes. Means this is a nightmare for anyone who has done it. But here, just a point clouds, I'm done. No structured mesh needs to be generated, or unstructured mesh needs to be generated. So it's a meshless method in principle. You'll see that there are caveats to that. The second thing is that it's easy to implement, but this you'll see in the exercises how easy this is going to be. I am not someone who likes to code live in class. Ben is going to do that probably next lecture. So it's very easy to implement because all that you do is that you compute these residuals through backpropagation and you add it to the loss function. So this is very easy to implement. And the last thing is that it is scalable. And what do I mean by scalable? I mean it in a very particular sense. First of all, it is scalable dimensions. Because remember that generating a grid in 3D is complicated. In 4D, just storing the things is going to be extremely prohibitively expensive. When a 10 times 10 times 10 times 10 regular grid in 4D is quite computationally extensive. In 6D, it becomes almost impossible, right? But if you just have to generate a cloud of points, then you just random, this is the advantage, those of you know this, randomness works very well with very high dimensions. So if I tell you, give me 1,000 points in 100,000 dimensions, any Monte Carlo simulator is going to give it to you very easily. Whereas if you generate a grid in 100,000 dimensions, this is in principle impossible, right? So this is the big advantage, that in terms of dimensions, these algorithms are eminently scalable. So that's one of the promises. As you see, I didn't use the fact, I just used random points. So random points can be used in 100 dimensions, 1,000 dimensions if you want. Of course, there are limitations. After all, we're using pseudo-random number generators, and somewhere it breaks down, but not at 100 dimensions, 1,000 dimensions. Second thing is that it's scalable to different PDEs. And this is what you'll see, not so much today, but in the next lecture, when next couple of lectures, Ben will give you examples of different PDEs for which this can be done. I'll just give you one simple example just to illustrate it. So I did it for the heat equation, but suppose I had a slightly different equation. Let's say the Burgers equation. Burgers equation. So this is a sort of a toy model for, or at least it was invented as a toy model for Navier-Stokes. Even the Burgers himself realized that it was far from the case. So what is Burgers equation? Burgers equation is the same as heat equation. So except for one extra term. So heat equation is when you don't have this term, right? So this is a new term that you introduced, which makes it nonlinear, right? So this is a nonlinear equation, and this is a very, very important PDE. Now to implement the Burgers equation, instead of the heat equation, all that we have to do is we have to evaluate one extra term, but that term in principle has already been there. Remember, whenever I defined the neural network, I had u theta, right? And in order to compute uxx, sure as hell, again, I need u dx of u theta. So these objects were anywhere there in the computation of the second derivative. So all that I do is that I multiply them and I add an extra term here, plus, should be there, u theta dx of u theta. Easy, right? So then everything else is done by the loss function, nothing changes. So very simply, you can go to Schrodinger's equation if you want, you can go to whatever KdV equations if you want, Navier-Stokes. Very complicated equations are trivially implementable, as you will see yourself in the exercises as well as in the class, but they are very easily done in this framework. So it is scalable it's not scalable in sort of a computational sense that I meant. It is sort of scalable to different domains of PDEs. So these are the main advantages of PINs, and that's why thousands of papers can be written, and we will study them for a couple of lectures. Let me just remind it so that you just to complete the story. Let me introduce some notation and sort of define them properly. So forget about these Banach spaces and so on. That's not important. What we need is, in order to do any kind of work, we need to work with some sort of an abstract setup, right? So this is for me an abstract setup for a PDE. This can mean anything. This can be whatever, heat equation, Navier-Stokes, Einstein, whatever, right? So this can be what it is. But remember that this is a differential operator. Okay, so it has derivatives in it. So d of u is some nonlinear function of u, the gradients, the second derivatives, and so on. So this is the basic local nonlinear function. So you can evaluate it through backpropagation. And then all the inputs to the problem are given through my source term f here. So in particular, I forget about the boundary and initial conditions, just to simplify notation. Okay, so now remember that this is the notation for deep neural networks, that after all, these are functions. Y, for instance, you can think of as xt. So instead of writing xt repeatedly, I just club them into Y. So we have deep neural networks here, just a multi-layer perceptron. And this is a structure, so we have activation function. And this is the first thing to remember, because we are taking second derivatives, sometimes third derivatives. I think we have even taken fifth derivatives. People have done like 8 derivatives and so on. So you have to differentiate many times through your, not once, because in a gradient descent algorithm, usually like Adam or something, you differentiate once. But here you have to differentiate many times to evaluate the PDE loss. So for instance, this is the first thing, that in the activation function, don't use ReLU. Now, who will tell me why you shouldn't use ReLU? Don't use ReLU. Maybe I'll ask him. Yeah. Yes. And if you second, it's okay. If you have non-differentiable point once, it's almost everywhere differential. But if you take the second derivative, suppose you want to do dxx of dyyy of this, then you are in trouble, right? Because then you have to differentiate again. So ReLU is something that is usually not used, but you can use sigmoid, you can use tan hyperbolic, or smooth ReLU, smooth versions of ReLU, the diameters of these activation functions. So in terms of architecture, this is the only thing that one has to remember, that instead of having ReLU, which is a very common choice, or any kind of ramp type functions, all that you have to do is that you replace them with something which is smooth. Okay, other than that, you don't need any changes in the architecture. The key point here is that, again, the idea is the same, that we have to find a neural network which is going to approximate my exact solution. Right? So this is the basic idea. And the main point is to be able to compute this by automatic differentiation. So that's why this local structure really helps, because then you can differentiate and you can find. So this is the residual, which is defined. And Y, for instance, you'll see in a minute what they are. So this is at any point. So, and finally, what pins are minimizers of this loss function. So remember that all that you do is that you change the loss function, right? Nothing else. So this is sort of the name of the game, that you change the loss function. But the loss function has to be sort of done over the entire domain. So where is the picture here? So it has to be done over the entire domain, which means that at the end of the day, I have to do what is called a quadrature loop. So Monte Carlo in particular is a quadrature. Or in other words, instead of just doing half, for taking points from half the domain, I have to take them from the entire domain. Okay, so this is where I need a quadrature. And we need to do some formulas. This is, you have to implement them at some point. So you need formulas. So in particular, this is some norm. It could be P could, for instance, be 2. It's a typical choice. Okay, so now you need so ideally, this should be an exact PDE loss. Let's call it as an exact PDE loss. But nothing is exact. We can never integrate exactly, right? We know that if I give you a complicated integral, you can't integrate it, right? So we need to replace this integral here by a quadrature, which is an approximate integral. So in other words, you choose some quadrature points. So these could be random, may not be random. You could also have structured points or quasi-random points or whatever. And then you form this loss function. And then you are going to sort of minimize for this loss function. So everything remains the same. All that changes is the loss landscape, because the loss landscape now has these PD related terms. And when you, not in the next lecture, but the lecture after, Ben will tell you how difficult, how this small change makes a huge difference, because it affects the trainability. So you still have to train this object to be small, right? So this is somehow the code here. So remember that you have to minimize a very high dimensional non-convex loss function as with the neural networks, but with this caveat that it's not just a supervised loss. You have some additional sort of PDE type loss functions in there. So is this clear now? So the algorithm is very simple. Set up your neural network, put your quadrature points, evaluate your losses, minimize. Right? but the devil will be in the details. Means it's not like something that is going to work. Many people think so, that okay, it's so simple that I can take any complicated PDE that I have and I put it in this setup and I get reasonable answers. But that's not always the case. So the question is, do they work, right? And of course, in many cases they do, many cases they don't, and you are going to see both. So now what I'm going to do is I'll show you some numerical experiments with a multidimensional heat equation. What do I mean by that? Remember that ut is equal to Laplacian d of u. And what is Laplacian d of u? This is sum over j from 1 to d of ux j xj. Okay, just a Laplacian, but now it's a parameter as per dimension. Because if you remember, in the first half of today's lecture, I showed you how the error of a traditional numerical method is going to increase exponentially, or the computational cost is going to increase exponentially, depending on what you keep fixed. Okay. So now what I'm going to do is I'm going to solve this with pins for one particular type of initial and boundary conditions, zero boundary conditions, actually, if I'm not mistaken. So this on the domain is zero, but some initial conditions, some specific initial condition. Don't ask me because I don't remember now. Roughly, I remember what the initial condition is, but I don't remember it at the moment. So then I just take as my pin, as my architecture, I just take an MLP, nothing fancy with the architecture, and I take it with depth 4, width 20, and now I'm going to pick and I'm going to fix the number of points, the quadrature points or collocation points, as people call them. And I'm going to take a lot of points, but I'm also going up to 100 dimensions. So it's reasonable to take a lot of points. So I'll take 16,384. That's 2 to the power 16, and in the interior, and 8,192 on the boundary. Or maybe it's 16,384 and 33,000 something, whatever. A lot of points, but just imagine if you had a grid in 100 dimensions. Even if you take 2 points in each dimension, 2 to the power 100 is not the same as 2 to the power 16, right? So this is unfeasible. And I'm going to solve it. I'm going to fix my architecture. I'm going to fix my number of training points. So the computational cost is going to be fixed. And I'm just going to explore how the error changes with dimension. Remember, for a traditional numerical method, this is going to blow up exponentially. So 4 or 5 dimensions is at most what you could do for the heat equation. There are other methods though, so one could cheat here. So in one space dimension, of course, the generalization error is also, let's call it as total error. Because this is, not only are the training errors tiny, but the errors are really, really tiny. So I could, of course, there's a lot of points though. So I could solve this with less than 0.10 to the power minus 3, 10 to the power minus 4 accuracy in no time, right? So this is a very, very small piece of error. And up to 10 dimensions, this is a very, very small error. You're still sort of less than 0.03%, which is nothing. But then the action starts when you are like in 20 dimensions. Now, traditional numerical methods have no chance. In 20 dimensions, how are you going to do that? But here you get less than 1% error with the same architecture. If you change the architecture, you get, if you make it deeper, wider, take more collocation points, then you're going to get less error. But this I'll take any day. Similarly, with 50 dimensions, you get 1.5%, 100 dimensions, 2.6%. I think there was a master's student a couple of years ago who did all the way up to 500 or 1,000 dimensions. So the error does, at best, it grows linearly. You can see that it's sublinear growth versus exponential growth, right? So this is brilliant because it is able to do this in a sublinear manner rather than in an exponential manner. So there yes, go ahead. Because we know the exact solution. Otherwise, how else are we going to, so in this particular case, we know what the exact solution is. We have an exact solution for the heat equation. Remember, it's a linear equation. So if you just define it on a square, it's not so hard to come up with an exact solution. So we know what the exact solution is. Any further questions? Please interrupt and ask me what happens. So this seems like a super success, right? We are able to solve a 100-dimensional problem, and it doesn't take long either. I think the training time was like 20 minutes or something. So it's 100 dimensions. This seems particularly impressive, right? So now the question is, do pins work? Means they do work, at least in this particular case. Next lecture, you'll see many other examples of do they work. But then the question is, when and why do pins work, right? So now this is what I wanted to do. But okay, let me at least explain what it means. What do we mean by when something works, right? So essentially, the aim in all these algorithms is that we have an exact solution, which is U. We have our pins solution. Let's say pins is U theta. And remember, by pin, I mostly mean that the training is, yes, go ahead. Yes, please. Yes, yeah. It would be great if my one-dimensional net is going to, but here there is no such thing, right? Because remember that there is no way that the one-dimensional heat equation is going to solve. It's not even defined on the same domain, so you cannot do that. So remember, the inputs are always going to be x and t. T is common, but x changes, right? From an interval to the unit square to the unit cube to the 10 hypercube to the 100 hypercube and so on. So there is no choice but to do this. Yes, go ahead. Yes, very much. So the initial conditions are part of the model's input. The boundary conditions are 0. So they, of course, also a part of the model's input because in particular, you're trying to minimize that, but the initial conditions are also part of it. Otherwise, how else you to get a solution for the PDE, you need both. Otherwise, the PDE is not uniquely or well posed. Okay, good. So now what does it mean for something to work? So it depends on how you define metrics, right? So all the time you have to define the right kind of metrics. So here the relevant metric, at least to me, is what is called the total error. Okay, so what it means is that you take your original exact solution U, you take your pin U theta, let me call it as U theta, you take the difference and then you norm them in some norm. You can think of it as L2 being the simple example. And remember that in supervised learning, we would always be trying to minimize this sort of mismatch with the ground truth. But here we don't have the ground truth, right? We don't necessarily know the exact solution. On the other hand, all that we have is the PDE residual. Okay, so this term here, this PDE residual, sometimes people call it as generalization error. This is, let's call it as a PDE residual. But in practice, we don't even have access to this. Why? Because this is a norm, which means that this is an integral over the whole domain. And of course, we don't know how to integrate. So we only have access to a quadrature version of it, which is what is called as the training error. Okay, this is what we can monitor during our training. And this is exactly what I showed you. Actually, as you can see, the training error, okay, at least in the high dimensions, it didn't change much. It was still a very, very small number, even though the total error did increase exponentially. So this is the only number on which I have control on. I don't know what is the exact solution. I know what the boundary conditions are. I know what the initial conditions are, but I don't know what the exact solution is. But I can monitor the training error. How much is the residual minimized at the training points? That's all that I know, right? So now the theoretical questions that come in, and at some point we'll answer them, but I just at least state them. I don't have the time to answer them today, even though I wanted to, is the following. So the first thing is, at the end of the day, you want to minimize the error, right? So you want to minimize this quantity here, E. But you don't have any access to this. The first question is just like universality, the fact that, so our entire algorithm leverages residuals, right? So can we say that we can make the residuals as small as possible? In particular, can we make the training error as small as possible? In principle. In practice, we may or may not be. So in other words, in this very complicated loss landscape, do I have a global minimum, which is going to say that this is a very, very small quantity, right? So this is a question of trainability or feasibility of training. So that's one thing. The second thing is, so in particular, so we only have control on the residual. Does it automatically imply a small total error? And this will be true if the residual, if you have an estimate like this, if we say that this quantity goes to 0, then this will automatically go to 0, right? So I can minimize the residual, then my total error is going to 0. And finally, I don't have access to this. I only have access to the training error. And the number of collocation points. In other words, as the number of collocation or points that I have, quadrature points, If these guys go to 0, and if the training error goes to 0, then if I can control this, then I can leverage it to control this. Okay. So the path in which one has to sort of argue is that a small training error, which is the only thing that I have control on. First of all, it should be possible to reach a small training error. It need not be the case. In fact, you will find that it's often not the case. That's why pins are not going to work in many cases. But first, I can target a small training error. A small training error and sufficient number of quadrature points, does it automatically imply that my residual is going to be small? That's the first question. And then if the residual is small, does it mean that the total error is small? Okay, and these are things that I will touch upon at some point, not in the next lecture, but in a few lectures hence, after you have seen several examples of pins and also seen where they fail. Okay, so with this, I stop here. And in the next lecture, Ben is going to continue. He's going to give several different examples for pins for different kinds of PDEs. That's the next lecture. And the lecture after, he'll also show you some limitations. And the limitations is when the training probably fails, right? Because this suggests that the training can fail, or the PDE is so complicated that it's very difficult to get the solution. And you'll see that. Okay, so I will meet you in 3 weeks because that's when I take over from Ben. Until then, so long. Okay.